Welcome to the Exam 2 review problems. So these problems are designed to supplement the additional work that you're doing in preparation for Exam 2, where you can see me go through some solutions to problems that are similar to ones that we've done in class, things on the study guide, on the homework, etc. So we're going to start off with our first problem here. Determine whether the set S, which is a polynomial of this form, 2x cubed plus bx plus a, where a and b are real numbers. Determine whether this set forms a subspace of P3 of R, which is the vector space of all polynomials of degree 3 or less. So S definitely is a subset of V, but does it form a vector space in its own right? So the actual solution to this can go very quickly if you remember the zero vector check. Every subspace of a vector space has to have the zero vector in it also. If it doesn't, it cannot be a subspace. So notice the zero vector in P3. So the zero vector in P3 of R is 0. It's just like the number 0. But 0, for this form of the polynomial, we can let a be 0 and b be 0, but that 2 will always stay a 2. So 0 cannot be in the set S. Thus, S cannot be a subspace. So if the question asked exactly this, does it form a subspace or not? The answer is no. It cannot be a subspace because it fails the zero vector check. Now, for the sake of our practice, that's not particularly interesting. I want to go through the process of checking closure under addition and scalar multiplication and show that those don't work also. So you can see what the process looks like more in full. So we're going to check A1. So closure under addition, that first axiom. So we need to establish some vectors in S. So we're going to let P1 of x be a polynomial of this form. So we'll do 2x cubed plus b1x plus a1 be an element of S. And P2 of x, that'll be 2x cubed plus b2 of x plus a2 be an S. So we're establishing two vectors that are both in the subset. The question is, does their sum also fall within the subset? So then P1 plus P2 of x, which is just P1 of x plus P2 of x. That's going to be 2x cubed plus b1x plus a1 plus 2x cubed plus b2x plus a2. If we combine like terms, we're going to get 4x cubed plus b1 plus b2x plus a1 plus a2. Now, these terms, because a1, a2, b1, and b2 are all scalars, this part does match the form of this. You have a scalar times x plus a scalar. However, the first component to be in S has to have a 2 in front of it. This one has a 4 in front of it. So this does not match the form that it would have to be in S. So this is not an element of S. So we can say, thus, S is not closed under addition. And again, to answer the question, is it a subspace, that would also be sufficient by itself to say, no, it's not. If the question asked us to check A1 and A2 regardless. We would still have to go through this process, but again, you wouldn't have to do the whole thing if the question is asked like this. I'm just doing it for the sake of extra practice. So again, we don't need to check A2 here because the question doesn't ask us specifically to, but if we were going to check it, we would go ahead and establish a vector. So let P of x be 2x cubed plus bx plus a, and establish a scalar. So let k be any real number. Then, if we take k times p of x, so that's k times p of x here, that's k times 2x cubed plus bx plus a equals 2k x cubed plus kbx plus ka. And we have a similar problem happening here. Kb and ka are fine, so those are still just all scalars. So those still match the form. However, this coefficient right here, the 2k, that has to be 2 for all real numbers, k, but it's not. It's only true if k is 1, but that's only one out of infinitely many different numbers. So this is not in S for all k in R. Thus, S is not closed under scalar multiplication. Okay. And any one of these conditions, again, would have been sufficient to say that it's not a subspace. So therefore, S is not a subspace of V. So just be careful to check and make sure that you know what the question is asking you for. If it's just asking, is it a subspace, you can just use any one of these to show that it's not. But if the question is asking you to verify or check A1 and A2, then you would still need to do them both regardless of whether they succeed or fail. Let's move on to the next example. So we're going to try our hand at a little bit of proof writing here. So suppose that the set v1, v2, v3 is linearly independent. Let w1 equal v1, w2 equal 2v1 plus 3v2, and let w3 be 4v1 plus 5v2 plus 6v3. Show that the set of w vectors, w1, 2, and 3, is also linearly independent. So, to show the set of vectors is Li, we need to assume that we're setting up a linear combination. So C1, W1 plus C2, W2 plus C3, W3. Assume that that's equal to the 0 vector. And we need to show that C1, C2, and C3 are all equal to 0. So if C1, C2, and C3 must be equal to 0, that means that none of these vectors can be written as a linear combination of any of the others, okay, which is what it means to be Li, right? Because if I could write W3 as a combination of these two somehow, that would be LD, linearly dependent. So if we can show that C1 through C3 are all 0, that proves that this set is Li. Now we know some things about W1, 2, and 3. We have these relationships defined in the problem. So let's go ahead and substitute. So we're going to get C1 V1 plus C2 times 2v1 plus 3v2 plus C3 times 4v1 plus 5v2 plus 6v3 equals 0 vector. Now, algebraically, what we can do is we can distribute these constants to each of the vectors and regroup by vector. So I want to group all of the v1s together, and then group all the v2s together, and group all the v3s together. So distribute constants and regroup by vector. So if we look at all of the v1 terms, we're going to have c1 plus 2c2 plus 4c3. And all of those are times v1. Plus, now for v2, so nothing here, there's a v2 right here, so that's going to be 3c2 plus, we've got 5c3 times v2. Now for v3, there's only one of them, that's right here, so we're going to get plus 6c3 v3, all equal to the 0 vector. Now, we haven't used our other given information yet. This is where this is going to come in. So suppose that this set of v vectors is linearly independent. If this set is Li, that means that this linear combination that we've just come up with, so think of this as if it's taking the place of like a C1, this would be like a C2, this would be like a C3, but not exactly because not those same letters. But we have a constant times v1 plus a constant times v2 plus a constant times v3. Because this set of vectors is Li, we know that these constants have to be equal to 0 in this form. So since this set of vectors is Li, that means C1 plus 2C2 plus 4C3 must be 0. 3C2 plus 5C3 equals 0. And 6C3 equals 0. So each of these coefficients in the linear combination must be 0 because the set of v vectors is Li by definition. But this gives us a system of equations, right? So this sum equals 0, this sum equals 0, and this equals 0. You can set this up in a matrix if you want to, but you can also look and see like the solution is fairly clear here. This equation tells us that C3 has to be 0. If C3 is 0, that means C2 has to be 0. And if both of those are 0, that means that C1 has to be 0. So the only solution to this system of equations, so the only solution to this system of equations is that C1, C2, and C3 all equal 0. And if you recall, that is exactly what we needed to show in order to prove that the set of W vectors is Li. Because this C1, C2, C3 are the same as this C1, C2, and C3 up here. So we can go ahead and say, therefore, this set W1, W2, W3 is Li. Found by essentially using the same definition twice with some algebraic manipulation in between. and solving a system of equations. This system, again, was already in a form that we could solve it without a matrix, but you can also set up a matrix and see that you do end up getting like a pivot in every column, one unique solution. It's all zeros. Moving on to our last problem here for this video, jumping ahead to chapter 6. Consider the linear transformation T going from M13 of R to M31 of R, defined by T of A equals A transpose. So the transformation is saying take a matrix and transpose it. That's how you transform it. And we're transforming 1x3 matrices into 3x1 matrices. We want to find bases and dimensions for the kernel of T and the range of T, and determine whether T is 1-to-1 onto both or neither. So for part A, let's look at the kernel of T first. So the kernel of T is going to be elements of the input vector space. So those are 1x3 matrices. So that'll be ABC, like that. We'll just keep it totally arbitrary. The kernel is the set of all 1x3 matrices such that the transformation of that 1x3 is the 0 vector. So that would be, right, ABC, like that. That's a 3x1. That would have to be the 0 vector, or the 0 matrix, if you like that. So the kernel consists of all 1x3 matrices here that when we transform them by taking the transpose, give us the 0 matrix over here. But the only one that will transform to give us all zeros is all zeros, right? When we transpose, we don't change the value of A, B, and C. So if they're going to be 0 here, then they had to have been 0 here as well, right? There's no other way to make these 0. So the only vector that transforms to 0 is the kernel of T, 0, 0, 0. So the basis is going to be the set of all vectors that are Li that span this, but it's just the 0 vector, so we just end up getting, again, the same thing. So this is the 1x3 0 matrix. So this is the basis. And then thus the dimension of the kernel of T, because the kernel of T only contains the 0 vector, we say that its dimension is 0. So that's our kernel. For the range, so the range of T, that's going to be the span of a transformed basis for all 1x3 matrices. So that's going to be transformation of 1, 0, 0, of 0, 1, 0, and 0, 0, 1. It can be any basis for M13, but the standard basis really is the best and the simplest way to go. So if we transform each of those, we do so by taking the transpose of them. So really we're just turning them from rows into columns. So we get 1, 0, 0, 0, 1, 0, 0, 0, 1. So the range is the span of these. Okay. Now, if we're looking for a basis, not only do we need to span, but we need them to be Li. These vectors are clearly Li. These form the standard basis for 3x1 matrices, right? So these vectors are Li. If there was more of a question about whether they were Li or not, we could test them to see if the set is Li, and then potentially eliminate any unnecessary dependencies, right? So like if these vectors were different and we found that the third one depended on the first two, we could go ahead and get rid of that to create a basis with only two of them. That's not the case here, though, because these vectors clearly do not depend on each other. So basis for the range will just be, again, that set of 3x1 matrices. And thus, the dimension of the range of T equals 3. Now, notice, actually, that the span of these vectors, I mentioned that these form the standard basis for all of M31. So if we're spanning all of that, it means we're really spanning all of M31 of R. So technically the range is all of M31, so it spans the whole vector space. And that bears out here because the dimension of this vector space is 3, right? 3 times 1. And the dimension of the range is also 3. So they're the same size, so the range covers all of M31. So that answers part A for bases and dimension for kernel and range. For part B, determine whether T is 1-to-1 onto both or neither. Well, we've already done pretty much all of the work that was necessary to make this argument. So since the kernel of T equals the 0 vector, and only the 0 vector, T is 1-to-1. And since the range of T equals M31 of R, so it covers the entire output vector space, T is onto. Thus, T is both. You could also use dimensional arguments. We know that M13 and M31 are the same size, right? They both have a dimension of 3, which means that it is going to be either both or neither, right? This is an isomorphism if it's both. That would tell us that all we would need to do is check one or the other. If one of them succeeds, they both must succeed. But if one of them fails, then both of them would fail because those dimensions are the same. Okay, and again, the dimensions being the same does not guarantee it's an isomorphism. We still have to check. But in this case, we already had to do both anyways. So we already found the kernel. We already found the range. So both of those arguments satisfy our conditions here. So it is on 1-to-1. It is on 2. So it is both. And that brings us to the end of our exam 2 review problems. Hopefully you found this helpful and a little bit insightful. Reminded you of some things maybe you had forgotten or you saw something new here. But good luck with the rest of your preparations for exam 2.